Hello guys, let's have a look at this current question. So here we have an FAQ on electricity and magnetism, specifically the topic of electrostatic forces and fields. So let's start. A charge plus Q is uniformly distributed over a quarter circle of radius capital R as shown above. Points A, B, and C are located as shown, with A and C located symmetrically relative to the x-axis. Express all algebraic answers in terms of given quantities and fundamental constants. Let's move on to part A of the question. Rank the magnitude of electric potential at points A, B, and C from the greatest to the least, with number 1 being greatest. If 2 points have the same potential, give them the same ranking. We know that the formula for electrostatic potential V is given by the formula V is equal to constant K into Q divided by R. Here K is the constant of proportionality, whose formula is 1 by 4 pi epsilon naught, and value is 1 into 10 power 9 into 10 power 9. Sorry. So capital Q is the source charge producing the potential at a given point, and R is the distance. We understand from this formula that V is inversely proportional to R. And since we observe that B is the closest to this source charge plus Q, the potential at B will be the highest, giving it a ranking of 1. Since A and C are symmetrically equidistant from the charge plus Q, we understand that the potential at A and the potential at C will be equal, giving them both the ranking of 2. Moving on to the next question. Point P is at the origin as shown below and is at the center of curvature of the charge distribution. Determine an expression for electric potential at point P due to charge Q. Now let us answer part B of the question. So the part B asks us to calculate the value of potential V. I know that potential V is given by the formula V is equal to integral of constant K into the differential of charge Q divided by R. I know that differential of Q here can be written as D into Q is equal to lambda into R into D theta. So I can rewrite this equation as V is equal to integral of lambda K, into lambda into R into D theta by R. R and R cancel each other. And I know that lambda is a linear charge density, which I have assumed to be the total charge Q divided by the total length R. But since here the length is an arc, the length of an arc is given by the formula length of the arc S is equal to R into theta, where R is the radius, theta is the angle substituted. Let us assume for our sake that the angle substituted is a perpendicular angle of pi by 2. So assuming that you have S, length of the arc S is equal to R into pi divided by 2. So you have the length of the arc length here as R into pi divided by 2. Substituting this in the integral, we have voltage or potential V is equal to integral. Now under the limits 0 to pi by 2, we can afford to take 0 to pi by 2 as potential V is a scalar. Writing further, K into capital Q dQ or d theta, into divided by R into pi divided by 2. Moving further, we understand that potential V can be further simplified and written finally as V is equal to K into capital Q divided by R. Let's move on to the next question. A positive point charge Q with mass M is placed at point P and released from rest. Derive an expression for the speed of the point charge when it is very far from the origin. We understand that a small charge or a test charge of small q is placed at point P. And when it is placed at point P, the potential energy for a system of charges U is given by the formula K into charge Q1, which is the source charge capital Q here, and charge Q2, which is the test charge Q here, divided by R, which is the distance between them. So here potential energy U becomes K into capital Q into small q divided by R. We understand that this potential energy is what subsides as the kinetic energy for the charge Q as it moves farther away. So this potential energy is equated to the kinetic energy of the charge small q as half m v square. Rewriting the formula in terms of v, we get v is equal to 2 into k into capital Q into small q divided by m into r whole under the root or a square root. Moving on to part D. On the dot representing the point below, indicate the direction of electric field at point P due to charge Q. Now let us take a look at the question. We understand that there is a small infinitesimal charge delta Q at this point, which applies a field in this direction. A small charge delta Q in this point, which applies a field in this direction. The resultant of these two vectors is exactly through the center. A similar case can be provided or made for the charges here and here, and here and here, and here and here, and so on and so forth. Thus, we conclude that the resultant vector addition of all the vectors of all the electric fields acting on all the infinitesimally small charges distributed uniformly along the length of this arc is a resultant electric field that is acting towards the right. So we understand that the resultant electric field acts towards the right in this direction. So this is the direction of the electric field due to this uniformly distributed charge capital Q. Moving on to the last part of the question. Derive an expression for magnitude of the electric field at point P. So we know that electric field E, the total electric field E is given by the formula E is equal to integral under the limits minus pi by 4 to plus pi by 4. The reason we are changing the limits from 0 to pi by 2 to minus pi by 4 to plus pi by 4 is simply because electric field is a vector. Minus pi by 4 to plus pi by 4 v d theta. V dr to be specific. dq to be specific, sorry. dq. Now, dq can again be substituted as lambda into r into d theta, where lambda is written as q by r into pi by 2. Substituting and simplifying further, we get the value of electric field under these limits to be 2 root 2 divided by pi into k into capital Q divided by r square. This concludes the answer to the question.